Hello everyone, welcome to this week's virtual discussion. I am Xinrui, and I will take you through problem 1. In this problem, we want to give a combinatorial proof of this identity here. This identity is referred to as the hockey stick identity, because the way that the binomial coefficients involved are arranged like a hockey stick in the Pascal triangle here. So to write up combinatorial proof, we must identify a set S that we can count with both sides of the identity. In this case, we're going to consider a cup with n red and n+1 blue marbles, and then let the set S to be the set of all distinct arrangement of these marbles into a line. So now, let's look at problem A here. It asks you to explain how the right side of the identity, which is this quantity here, counts the set S. Please pause the video and think about it. Now, let's look at the answer of this question. So here, because we have n red marbles and n+1 blue marbles, n plus n plus 1 just refers to the total number of marbles. And because all the red marbles are the same and all the blue marbles are also the same, we just need to choose the positions for the red marbles to count all distinct arrangements of these marbles. Here, so n refers to the number of positions we choose for the red marbles. You might approach this problem in a different way and think about choosing the positions for the blue marbles instead of the red marbles. And you write something like this. Here, the top one still refers to the total number of marbles. But here, down here, the n+1 refers to the number of positions for the blue marbles. And as what we know about the binomial coefficients, we can find that this value here and here are actually the same. So this shows you that no matter you count up the positions for the red marbles or you count from choosing the position of the blue marbles, you will always explain why the right side counts the set S. So now, let's reason about the left side of the identity. Here, we need to figure out what's the meaning of the variable k. One way to think about k is that k represents the number of red marbles to the left of the rightmost blue marbles. So in other words, for each of the sequence in problem B, we first need to identify the rightmost blue marbles, and then look at the left of it and see how many red marbles are there. Pause the video now and think about problem B. Now, let's look at the answer together. For the first one, the rightmost blue marble is here. And to the left of it, there's only one red marble. So k equals 1 here. For the second one, the rightmost blue marble is here. And to the left of it, there's 0 red marble. So k equals 0. For the third one, the rightmost blue marble is here. So to the left of it, there are 1, 2, 3, 4 red marbles. So k equals 4 here. And for the last one, the rightmost blue marble is this one. And to the left of it, there's 1, 2, 3, 4, 5 red marbles. So k equals 5 here. Now, let's look at problem C. It asks you to find all the possible values of k. pause the video now and think about it. Now, let's look at the answers together. So, as shown in part B, second example here, we know that the smallest value k can get is 0, where there's just no red marbles to the left of the blue marbles. And then let's consider another extreme case where all the red marbles, that is, the n red marbles, are placed to the left of all the blue marbles. So here are the remaining m plus 1 blue marbles. In this case, we place all the red marbles to the left of the blue marbles. So here, k equals n. And because we only have n red marbles, k can be n at most. So from this question, we find that k can be any integer from 0 to n. Now, let's look at problem D. It asks you to explain why there are exactly m plus k choose k arrangements associated with each value of k. Pause the video now and think about it. Now, let's look at the answers together. Here, because k refers to the number of red marbles to the left of the rightmost blue marbles, so let's just fix the rightmost blue marble first. So let's place a blue marble somewhere, let's say around here. Then let's consider what's the marbles to the left of this rightmost blue marble. First of all, because it is the rightmost blue marbles, there are m blue marbles to the left of it. So here, m blue marbles. And because k refers to the number of red marbles to the left of the rightmost blue marbles, there are also k red marbles here. Now, since we placed the k red marbles to the left of this B here, all the other red marbles must stay at the right of this rightmost blue marbles. Here, we can find that because to the right of this blue marbles, there's only red marbles there. So what's on the right does not change our arrangement of all the marbles. It's only what's to the left of this blue marbles that can change the arrangement of marbles. So essentially, here we are just trying to find how many different arrangements we can find for k red marbles and m blue marbles. Using the same similar reasoning here, we have first m plus k marbles, and no matter you're choosing the positions for the red marbles or the blue marbles, you will always end up with the binomial coefficient m plus k choose k. Now, that explains why there are exactly m plus k choose k arrangements associated with each value of k. Now, let's look at part E, which asks you to put the ideas from part D and E together to explain how the left side of the identity counts the set S. So here, the left side essentially just partitions the set S based on the number of red marbles to the left of the rightmost blue marble. To count how many elements are in each partition of the set S, we have the binomial coefficient m plus k choose k. And after we partition the set S, we use the addition rule. To add the number of elements in each partition of S together, which is the sum of k from 0 to n of m plus k choose k. Using this addition rule, we can obtain the number of elements in S. So this is how the left side of this identity counts the number of elements in S.
Hi CS2800 students, my name's Robin and I'll be walking you through the beginning of problem 2. In this problem, our old friend Alfred has bought a box of donuts, and in this box there are 6 different flavors with 2 donuts per flavor. We're trying to figure out how many different ways he can select 7 of these donuts to bring into his coworkers the following morning. Here, 2 selections will count as different if they disagree on the number of at least 1 flavor of donuts, and we should note that the order he chooses them and the way that they're arranged don't matter, so those don't count. Let's consider this proposed solution. We can use stars and stripes, treating the 7 selections as indistinguishable balls and the 6 flavors as distinguishable bins. Thus there are 7 plus 6 minus 1, choose 6 minus 1 equals 12, choose 5 equals 792 possible selections. So here what this person does is they pick 7 as the indistinguishable balls, so those are the number of selections. So we have n equals 7, and we have m, which is the number of distinguishable bins, equals 6. So those are the 6 flavors. So we know from lecture that the number of arrangements of n indistinguishable balls and m distinguishable bins is n plus m minus 1, choose m minus 1. So that's where they get this number from, the 7 plus 6 minus 1, choose 6 minus 1. Take a minute to work out a solution as to why this might not be correct, and try to figure out if this person has over or undercounted the number of possible selections. So take a minute and pause and write out a solution for that. Okay, did you pause? I hope that you paused. Okay, so I've drawn out, this is the box of donuts that he originally buys. You can see there are 6 different flavors represented by the 6 different colors, and there are 2 of each flavor. So the way that we write out a stars and stripes problem here, we have 7 stars, 4, 5, 6, 7, and the stripes are going to be kind of the boundaries between our bins. So say that we put a stripe here, we put a stripe here, put a stripe here, a stripe here, stripe here. So 1, 2, 3, 4, 5 stripes, because there are 6 different flavors. That would mean there are 2 of the first flavor, 1 of the second, 1 of the third, 1 of the fourth, 1 of the fifth, and 1 of the sixth. Okay. So the way that he does it, or she or they, actually overcounts the number of possible selections because they don't take into account the fact that this person only has 2 of each donuts. Alfred can't do something like this, where they only choose 7 of the first donuts and none of the rest of them. So clearly that approach didn't work. So let's try a new one that does. We're going to combine the stars and stripes method with the inclusion-exclusion rule. So let S be the set of selections of 7 donuts in a hypothetical world where there are 7 donuts for each flavor. So this would be that we're no longer restricted like we were in the last problem. What is the size of S? Take a second, work it out. So in this case, the last proof was actually correct. We have n equals 7, meaning we have those 7 donuts we're trying to give away, and m equals 6. We have 6 flavors, and we know that for n indistinguishable balls and m distinguishable bins, we have the total number of arrangements to be n plus m minus 1, choose m minus 1, which is going to give us 12, choose 5, which is that number we had before, 792 possible selections. So now we're going to subtract out all the bad events that can't happen from S. So let's define some things that are a part of S that aren't actually a part of our final solution. So what are 6 things that cannot happen for the 6 flavors in order to ensure that an element of S corresponds to a selection that Alfred can make? So take a second and try to figure out those 6 things. Well, in the first part, we saw that there's an issue when we choose more than 2 donuts of the same flavor. So let's make an event. We'll call it SI. And SI is going to be the event where more than 2 donuts, more than 2 donuts were selected from the same flavor. And we're going to call that flavor I. And since there are 6 flavors, we know that there are 6 events. There's S1, S2, S3, all the way to S6. So what is the size of S1? Remember that S1 is the event that more than 2 donuts of flavor 1 are selected. Pause and take a minute to work out a solution. Okay, so Alfred is choosing 7 donuts. And since S1 requires us to select more than 2 donuts for flavor 1, that means we have to select at least 3 donuts. So let's write this 1 here to symbolize that these 3 donuts are going to be of flavor 1. Now that leaves us with these 4 donuts. And since we know the order of the donuts don't matter, these 4 donuts, the placement of them is indistinguishable. So we're going to use a balls and bins approach where we're going to say that N, which is the balls, is going to be those 4 indistinguishable places that the donuts can go. So N equals 4. And M, which is our bins, are going to be the flavors. So there are 6 flavors. So the flavors are going to be distinguishable because we can tell the difference between something like this, 1, 1, 1, 1, or maybe something like this, 1, 1, 1, 2, right? Okay, so how many combinations can we have of 4 indistinguishable balls in 6 distinguishable bins? Well, that's the same formula that we've been using this whole time. We have that N plus M minus 1, choose M minus 1. Gives us the total amount of these arrangements. So that's exactly what we need for those last 4 donuts. So now we can just fill those in for N and M. So we have 4 plus 6 minus 1, choose 6 minus 1. And that is going to give us 9 choose 5, which is equal to 126 possible selections.
Hi, my name is Tia, and I will be walking you through questions E through G. So question E asks us what the cardinality of the intersection of S1 and S2 is. Take a couple minutes to think about the question, pause the video, and then we'll go over the answer together. So in order for S1 to happen, we have to have at least 3 donuts in flavor 1. And similarly, for S2, we have to have at least 3 donuts in flavor 2. So we can set these 6 donuts aside, and because we are picking 7 donuts in total, this leaves us 1 last donut where we need to pick a flavor for it. And since there are 6 different flavors, this gives us 6 possibilities. Now for part F, what is the cardinality of any j-way intersection of the bad events for j is greater than or equal to 3? Take a couple minutes to think about this, pause the video, and then we'll go over the answer together. So in order for us to have a j-way intersection of bad events, this means for j different flavors, we need to have at least 3 donuts of that, each flavor. Since we know j is greater than or equal to 3, This means that we have a total of 3 times j donuts that we need to set aside, where j is greater than or equal to 3, so this is greater than or equal to 9. But we don't have 9 donuts, we only have 7 donuts that we can select. So the cardinality of any j-way intersection of the bad events is 0. Now for the last question, we're just going to compute the actual number of ways that we can pick 7 donuts. We're going to do this using the generalized inclusion-exclusion rule, which is written right here. Take a couple minutes, see if you can figure out how to use the inclusion-exclusion rule, and then we'll come back and go over the solution together. So first, let's expand out this equation. We have the size of S, and then we need to subtract out a bad event for each of the 6 flavors. So this gives us a sum from j equals 1 to j equals 6 of the bad event. And then we have to add back our two-way intersections. And so this is as if we pick 2 different flavors, and then we have the intersection between those 2 different flavors being both bad. And then we don't have to add any more terms because any 3-way intersections, 4-way intersections don't happen, as we showed from above. So now we just have to plug in our numbers to this equation. First, we know that the size of S is 792 from above. And then the size of a bad event is 126. So our sum is equal to 6 times 126. And then lastly, the number of ways to pick 2 flavors is 6 choose 2. And we know that the intersection is size 6 because we computed it in part E. And this gives us a total of 126 ways that we can select donuts.